All right, so the problem that we're looking at is motivated by this model by Myers and Leskovich. So think that you have a cascade happening over a social network, and you see that at time one somebody's infected, then more people are infected, and then more people are infected, but you cannot actually see the graph. Okay, so you don't know what the graph is. So if this cascade is happening over the independent cascade model, and the activation time is exponential, then in fact the parameters of the model, so the infection probabilities from one node to another node, can be inferred through maximum likelihood estimation. And in fact, it's a convex optimization problem, so you can learn these things. And this is interesting because if you learn these, you can actually also infer the graph. So by seeing how the cascades happen, you can actually infer the graph. All right, so what we did here, the way that we extended this is that we looked at what happens if you incorporate priors on the distribution of the graph that you're learning. So if you believe that the graph that you're learning is actually a power law graph or has a stretched exponential distribution and so forth, how should you incorporate this in your optimization? It turns out that if you do this, you do not get a convex optimization problem. Nonetheless, it is a problem that you can solve with a majorize-minimize method, and each step involved ends up being a convex problem. And we show that if you do this, despite the lack of convexity, you get improved performance in inferring the graph. And my poster is back there between the two doors.
Hello, I'm San Quan. We are a team from CMU. Our topic is distributed community detection on age label graphs using Spark. So what is an age label graph? Here's an example. Each node represents an airport, and each line represents an air route between two airports. And each air route is hosted by a specific airline company. And the company name is what we call as an age label. And what we want to do is to find the community in this kind of graph. So how do we do it? We transfer this problem into a tensor decomposition problem. We representative age label graphs into a tensor, and then we propose a new type of tensor decomposition, which is a new kind of algorithm. Iteratively detect the factor vectors on original tensor. And this kind of algorithm is developed based on Sparks because we want the advantage of the Sparks of the scalability. According to our experiments, it shows that it can solve a bigger problem, and it demonstrates it can solve a 10 times bigger graphs compared to the single machine solution. And also, according to our experiments, if enough machines are provided, our system can provide speed out scalability. Yeah. So if you're interested, please stop by our poster just nearby the back. Thank you for listening. Thanks.
Hello, my name is Larry Holder. I'm from Washington State University. This is work I do with a colleague, William Eberly at Tennessee Tech. We've been working for a while on the problem of finding patterns and anomalies in graphs, and recently I'd look at graph streams. And the standard way of doing this is to, of course, divide the stream up into windows or batches, and then you run your algorithm on each batch and somehow try to accumulate those results. Well, for fast-moving streams, say for network traffic, you can't even do that because it's just too much data to, even each window is huge. So the main thing, so first of all, the definition that we use of an anomaly, it's not really an outlier. We look at normative patterns, and then we look for unusual changes to those normative patterns. So that's the type of anomaly we're after. So how do we speed this up even more? The main idea is to not run the pattern learning and anomaly detection until you have to. And so we looked at various different metrics over the graph stream, and we're looking for changes in those metrics. So as those metrics change, then we engage the pattern learning and anomaly detection. And it turns out that that speeds things up quite a bit, and it actually helps the anomaly detection because we're not changing the normative pattern so quickly, because the normative pattern can change based on noise in the stream, but if we don't do it too often, we tend to get more normative patterns and therefore better anomalies from that. So please come by my poster and we can talk more about it. Thank you.
Hello, my name is Arindam, and I'll describe this is a joint work with Shushmita from India Statistical Institute, and I'll be talking on graph analytics framework for ranking authors, papers, and venues. So basically, we consider the problems of how to assign scores and rank authors, papers, and venues. So there are many existing citation metrics like H-index, which tries to give scores to papers and authors, but they are very simplistic. They consider simple metrics like number of publications and number of citations. They don't really consider the underlying network structure of the authors, papers, and venues. So we consider this problem. This is basically a problem of ranking entities in a heterogeneous network. So we consider the the basic idea is very simple. Good authors tend to write papers, good papers in good venues, and so we consider the structure of the underlying collaboration network, citation network, and how the authors are publishing in papers and venues. So we have an iterative algorithm which computes the author scores, paper score, and venue scores based on their relationship with each other. We have run this algorithm on different data sets, and we found that the results are quite good compared to the existing metrics. And also we'll try to give some formal proofs that this algorithm converges and how to give the rate of convergence. In our earlier work, Citex, we were able to give the proof of convergence, but this is an extension where we are trying to still do that. If you are interested to more about the intuition behind this algorithm and how this algorithm works in practice, please visit our poster. Thank you.
Hello, everyone. My name is Dijing. I'm from University of Michigan. It's my great pleasure to present my work here. So this work is cooperated with teacher, and it's advised by Professor Danai Kocha and Professor Christos Flotousos. So it is called Pursuit 3. It is a large-scale graph mining tool through interactive data visualization. Pursuit 3 tries to answer research questions like how do we summarize different types of large graphs, and how do we find anomaly patterns in such graphs efficiently and effectively. So Pursuit 3 is an extension to its predecessor Pursuits in 3 ways. First, it provides rich types of graph summarization. Second, it provides strong capability of finding anomalous patterns. And third, it provides improved scalability in data. So in the upper figure, it shows the system workflow. Different types of graph statistics are calculated in a distributed manner using Pegasus, and they are finally stored in the backend database. Users can access and interact with such graph statistics by clicking on the dots in the distribution plots, and by examining the partial equinet and one hop adjacency matrix. In the paper, we showcase the results of running Pursuit 3 on these 3 different types of graphs. And in the poster session, I will try to illustrate the detailed mining process. Thank you.
Hello, I'm Nizreen Ahmed. I'm from Intel Labs, and this is joint work with colleagues from Xerox Spark, Ryan Rossi, and Rongzhu. And the problem that we are concerned here with is basically about relational learning on graphs, in particular prediction of node labels. And so what we are trying to do here is that we propose a flexible framework, semi-supervised learning framework that is based on maximizing similarity and generalizes across a spectrum of different collective classification methods. And it's extremely accurate and scalable. So my poster is all the way in the back, so please visit my poster. Thanks.
Hi, I'm EK from University of Michigan. So in this work, we have compared various graph clustering methods in terms of their summarization power. And also, we have proposed new parallel heuristics for the creation of graph summaries. So our summarization focuses on finding a succinct summary of input graph efficiently by employing the idea of minimum description length. And the summary would consist of list of structures in the model M here. And also, we encode an error matrix E. So the goal of our work is twofold. One is that we want to compare the summarization power of graph clustering methods. And to do that, we have used both quantitative and qualitative measures for the comparison. And the other goal is that we want to improve the summarization quality. And for that, we have proposed a greedy heuristic step with these parallel variants to speed it up. At the algorithm level, we have done a comparison with vote contrast, which has 3 steps. First, subgraph generation, and then subgraph labeling, where we give labels to the subgraph generated by the first step. And finally, summary assembly, where we select the structures to include in the final summary. So for more details, please check out my poster over there. Thanks.
Good morning, everyone. My name is Aman, and this is joint work with my colleagues Hao Han and Ramakumar. Network inference is an important problem in a variety of domains, and it refers to the problem of inferring interaction between nodes given some data about the network. There are different domains where this can be useful. Example, social networks and gene-regulated networks where you want to infer how genes interact with each other. Now, both the networks I just talked about are sparse in nature, where you expect one node to interact with only a handful of nodes. So both these problems can be cast as convex optimization problems. And there are a variety of techniques using which you can enforce sparsity in such problems. Like if you use L2 regularization, that kind of pushes your weights down but doesn't really add sparsity. If you use the lasso, you get sparsity, but lasso tends to be very brutal on your parameter weights and kind of selects only one feature out of a set of correlated features. A trade-off between both these approaches is the elastic net. And in this work, we actually propose to use K-support norm, which is a tighter convex relaxation of the L0 norm, and it's better than the elastic net for sparsity. And we qualitatively discuss how this norm in different settings can outperform the other norms I just talked about. So if you have any questions or comments about our work, please feel free to stop by our poster right at the back. Thank you.
Hi, my name is Yulia Gel. I'm from University of Texas at Dallas, and this is a joint work with Slava Ljubčić from University of Maryland and Leticia Ramirez from CIMAT. So in a nutshell, what we're interested in is evaluation, estimation, uncertainty on networks. So there are very many methods how you can, for example, estimate degree distribution and its functions, but very little is known about how you can quantify standard errors, how reliable your estimate, whether you can have some confidence intervals associated with your estimate. And so what we are doing, we are taking the ideas that have been developed for space-time dependent processes in statistics, and we are bringing those to random graphs and random networks. The idea is to take multiple agonets, so this is a sampling part, and then we resample all nodes within those agonets. And as a result, so first of all, we are able to provide confidence intervals that are reliable, that they are sharp, they are narrow, but still calibrated. We use only very small proportion of network information, so it's very information greedy, it's fast, and it's also valid for ultra-sparse regimes. Okay, and our poster is on that side.
Hi, I'm Olivia Simpson from UC San Diego. This is joint work with Julian. And we're looking at the problem of predicting risky behavior in a population. So for this particular problem, using individual features alone may not have enough information, it may not have the right information. And in particular, it might not include information about social influence, which can be really important for something like this. So we look at modeling risky behavior as a function of both individual features and network features. But rather than modeling these network features from the network directly, what we do is discover social communities. We uncover social communities by discovering communities that are associated with the risky behavior. So what we find is when we combine these two approaches together, we are able to better predict when compared to using individual features alone. So my poster's right over there. If you want to learn more about the approach and the results, you can find me on that side. Thanks.
Hello, everyone. I'm Xiang from University of Illinois at Urbana-Champaign. So all you can see, we have a lot of good work working on how to mine patterns and knowledge from the existing networks. But we also observed that in real world, a vast majority of the data that user generated is actually exists in the form of text data instead of network data. So we start asking the question about whether we can turn a massive amount of text data into some structured network that later on we can mine some knowledge from them. So as the very first step, we're trying to solve the problem of entity typing, which basically is trying to identify the entity mentions or the token spans of entity mentions in the text, and then trying to assign different kinds of types to those entity mentions. And the principle we're trying to solve this problem here is to leverage the massive text corpus so that they have a lot of redundancy in the corpus we can leverage. And then we're trying to leverage the existing knowledge base to get so-called distance supervision instead of asking human to try to label the corpus when we have a new domain to handle. So then the method we propose here can be flexible, applied to corpus of different domains as well as basically different languages here. In a nutshell, the work is trying to first identify entity mentions from the text and then trying to do some coarse-grained typing. So the methodology we apply to coarse-grained typing is limited when we're trying to dive into more fine-grained types, like hundreds of different types. So the next step to do the fine-grained typing, we're trying to leverage whatever syntactic features we have and jointly embed them to latent space and leverage that latent space to invert the types of each entity dimensions. So our poster is over there, so welcome to drop by and ask questions. Thank you.